Welcome back to The Explainer. Today, we're going to skip the whole what is a basic chatbot conversation. You guys already know that. Instead, we're popping the hood to see how AI is actually operating behind the scenes. We're looking at how it acts as this unprecedented accelerator for the most important scientific work of our time. We're talking everything from curing complex diseases to discovering brand new planets. So let's dive in and look at the actual tools the world's top scientists are using to reshape our reality. Okay, here's the roadmap for today. First, we'll look at the Great Research Accelerator. Then we'll move into AI toolkits and frameworks. Third, we're covering pre-trained AI models. And finally, we'll unpack the big debate between open source and open weights. All right, starting right off with Section 1, the Great Research Accelerator, where we'll see exactly how AI is supercharging scientific discovery. Thousands. Now think about what a traditional literature review looks like for a human researcher. Spending months, actually, scratch that, maybe even years, grinding through dense academic papers, just to understand the current landscape of a highly specific field. Well, large language models can now effortlessly synthesize thousands of these academic papers at once. They can instantly map connections between completely different fields of study and find crucial gaps in the literature that human eyes might have missed entirely. It's a fundamental, game-changing shift in how knowledge synthesis happens. And this is where it gets wild. Look at this breathtaking contrast in discovery timelines. In biology and chemistry, the timeline for discovery has literally collapsed. We are replacing a decade, 10 years of painstaking physical chemistry, physically mixing compounds in a wet lab, with just a few minutes of digital 3D protein simulation. AI tools can now accurately predict 3D protein structures. That means we can simulate molecular interactions to discover new materials and potentially life-saving drugs without ever picking up a single test tube. So as you can see, this supercharged pattern recognition is completely transforming how we approach humanity's biggest questions across vastly different scientific domains. In astrophysics, algorithms are sifting through unimaginable mountains of telescope data to successfully identify hidden exoplanets. In genomics, AI is rapidly sequencing DNA to pinpoint deeply hidden disease markers. And in climate science, deep learning models are analyzing complex historical weather patterns to simulate future climate change scenarios with extreme precision. The sheer scale of this data analysis is truly mind-blowing. Let's keep moving into Section 2, AI toolkits and frameworks. This is the heavy machinery. You know, when we talk about AI, we almost always focus on the final product, right? But we really need to understand the engines powering them. Think of these open source frameworks and libraries not just as lines of abstract code, but as the massive, heavy-duty industrial presses and conveyor belts of the AI research factory. These are the foundational tools researchers absolutely require to build, train, and test custom AI models from the ground up. Okay, here is your cheat sheet for the absolute heavyweight champions of AI frameworks and exactly what each one is built to do. If you're doing academic research in deep learning, you're almost certainly using PyTorch. It's developed by Meta, and it's the undisputed industry standard because it's incredibly flexible. Need to scale up to production-level machine learning? Google's TensorFlow is your highly scalable go-to. Then there's JAX, a newer favorite from Google Research, optimized specifically for high-performance math and scientific machine learning. Over in natural language processing, Hugging Face acts as the central hub for state-of-the-art models. And we absolutely can't forget scikit-learn, which is still the gold standard for your classical, traditional machine learning algorithms on smaller datasets. I just want to ground this for a second so we remember why this all matters. It's so easy to get lost in the tech jargon, but these frameworks aren't just abstract code sitting on a server somewhere. They are the exact, literal tools being used to model our changing climate and simulate breakthrough pharmaceuticals. Mastering JAX or PyTorch literally means holding the keys to our future survival and health. This is the workbench where tomorrow is being built. All right, Section 3, pre-trained AI models, or as I like to call them, the prefab brains. See, researchers don't always have to build an AI brain completely from scratch. In fact, they frequently download these pre-trained models to use as a brilliant baseline. They take these prefab brains and adopt them for their own specific, highly complex experiments. On the tech side, we've got large language models like Meta's Llama 3 family. These are state-of-the-art models heavily relied upon in clinical and legal research. You also have Google's Gemma providing lightweight, highly efficient models perfect for rapid developer experimentation. And then there's Olmo from the Allen Institute, which is a truly open-source model designed specifically to advance our fundamental scientific understanding of how LLMs actually work. And hey, it's not just text. Researchers are downloading visual prefab grains too, instantly unlocking incredible computer vision and spatial capabilities. Stable Diffusion is this massive open weights text-to-image model heavily utilized in generative media and spatial design research. Meanwhile, OpenCV is an open-source library just packed with real-time algorithms for object recognition and video analysis. So if a scientist needs their program to instantly recognize objects in a live video feed, they don't have to invent the math to do it. They just plug in OpenCV and get straight to the actual research. Which brings us to our final section, number 4, open source versus open weights. This is where we get to the catch.
So major tech giants absolutely love to throw around the word open, right? But many modern AI models are actually released as open weights. Here's what that means. You can download and use the final trained brain of the AI for free, which is amazing, but, and it's a huge but, the massive, incredibly valuable data sets that were used to teach and train that brain remain locked away in a corporate vault as proprietary secrets.
This excellently illustrates the massive gap we're currently facing in the scientific community. On the left, we have true open source. The code, the massive training data, the architecture, it is all completely free and public to modify, like that Olmo model we talked about. On the right, we have open weights. Only the final brain is free to use. The underlying training ingredients are totally hidden, which is the case with models like Llama. It's basically the difference between true open collaboration, where everyone can inspect the ingredients, and simply being handed a finished, mysterious tool that you aren't allowed to fully look inside. So as we wrap up today's explainer, I want to leave you with a bit of a provocative thought to ponder. We've seen how AI is undeniably the greatest research accelerator in human history, drastically cutting down discovery times for curing diseases and mapping the stars. But if the core recipes, the foundational training data for humanity's greatest discoveries, are kept as closely guarded corporate secrets, well, who really controls our future? How open is our science, really? Something to think about. Thank you so much for joining me to demystify the architecture of AI research. Keep asking those big questions, and we'll catch you in the next explainer.